It is. It is tough. That's the necessary evil. All right, so linear functions. So what is a linear function? A linear function is similar to slope-intercept form.
It is.
Yeah, thanks. Slope-intercept form, y equals mx plus b. When we put it in function notation, they change the y to f of x or g of x, h of x, some other notation there. But it still means the same thing. That m right there is the what of a linear equation. Slope. Average rate of change, slope. We did all that stuff. We talked about secant lines. They were linear equations in chapter 3. What's that b hanging out on the end there? The y-intercept. Again, we talked about that some in chapter 3. So nothing too crazy about that. Now, when you talk about a linear function, under normal circumstances, what would the domain of a linear function be? And if it helps, we'll write it, y equals or f of x equals 3x minus 7, something like that. What would the domain of that example be? Say that again, Luke. No, that'd be the y-intercept. That's not the domain. Domain, what's domain? All the x values. So what x values work for that problem? Are there any red flags? What red flags do we look for? A square root with x's inside, or a fraction with x's where? In the denominator. None of that's happening in this problem, so it doesn't have any red flags. If there are no red flags, then the domain is automatically what? All real numbers, negative infinity to positive infinity. Means the same thing. Okay? What would the range of a linear function be? We can use this example as the linear function we think about. This applies to any linear function. So range. Think about the graph of y equals 3x minus 7. Well, what numbers on the y-axis? What range is, it's the what y values were. So what does the graph of y equals 3x minus 7 look like? If we're not sure, we got a nice calculator. It does graphs. 3x minus 7. I'm going to hit zoom 6 to get back to my normal window there. All right, so there's the graph of 3x minus 7. What's the range of that? That's the y-intercept. What y values does the blue line use? Doesn't use just -7. Uses all of them. Okay? Y values. This graph continues forever going up, forever going to the south. So that is all real numbers again. Okay? Every linear function that is in this form, slope-intercept form, will have a domain that's negative infinity to positive infinity, all real numbers, and a range that's the same. Okay? There are exceptions, but they are not written in slope-intercept form when they're exceptions. Different. Okay? So, let's look at the first example. Find the function value. F of x is equal to 3x minus 7. Find f of negative 2. What does that mean? Absolutely. Good. We know that. F of -2 means plug in -2 for x and work it out. So it'd be -6 minus 7 is -13, right? So f of -2 is -13. That means what? What is f of -2 equals -13? What is that the same thing as? What's the ordered pair? There you go. Those are the same things. That notation, this is function notation with the f of -2 is equal to -13. The other one is the ordered pair notation. So they mean the same thing. You got to be able to bounce back and forth between those two. Okay. So finding function value when they give us an x value to find. Okay. Really easy to do. If I'm using my graphing calculator, I've got the graph already drawn, and I want to know what's the y value when x is -2. There's a couple of different ways to do that. One way is to hit the trace button, and then just type in -2. Look down at the bottom, gives me that ordered pair. So there's a shortcut with your graphing calculator that can help you. Drawback to that is if it ends up being a fraction answer, you're going to get a decimal spit back out at you there. Okay, so just understand that that's what happens if you use the trace function. If you want to use the table in your graphing calculator, you hit second graph, and then I'm type in -2 and hit enter, and it punches back out the -13. I could put in any x value in that table and get the y value that goes with it. Does the same thing as the trace, but if I were going to make a table of values or something like that, I had to make a table and I needed several x values, I could put them all in one step. Like if I needed -2, -1, 0, 1, 2. That's how we used to do it in Algebra 1. We would make you make that table first and then draw the graph. Y'all remember doing that? So if I needed that, I could do it with the table function on the calculator. If your calculator's not letting you type in those values, you got to hit second table set and make sure the independent is set to ask. If the independent is not set to ask, you can't type in values. Okay, so if it's letting you type in values, you don't have to change that. So second window goes to the table setup, and you just need to make sure the independent is set to ask, and that lets you type in the x values you want in the table. Okay. All right. So function value when they give us an x value. B part or section part or example B. Let's say it asks us to find x when f of x is equal to -21 or f of x equals 3x minus 7. Where's the -21 go? No. It's okay. I'm glad you will. Nobody else is. For f of x, it replaces the f of x. So it's like the y value. We want to find the x value out of that. So set it up with -21 equals 3x minus 7. You want to put the -21 on the other end, it's okay. And then to solve that equation, just good old pre-algebra stuff there. So that'd be -14 equals 3x. We divide. We're going to leave that as an improper fraction. -14 over 3 is the x value. Okay. If I go to my graphing calculator, remember that's the same equation I had graphed, right? And I hit trace, and then I type in -14 divided by 3. It changed that -14 over 3 to a decimal. I knew where it came from, so that's not what I'm worried about. And I'm checking to make sure that I get -21 as the y value. That just shows me, hey, I got it right. Way to go. You know, that sort of thing. Again, on the table, you do the same thing. You could type in -14 over 3 into the table, and it spits back the y value for you. So, several different ways of doing that. I generally, for simple equations like this, I don't normally use the calculator to do it, but I just want to show you all of those things because it'll help us later when we get to more complex equations to be able to do some of that stuff. All right. Insert a page here. I have it in there. I'm going to cut that. Put that on the next page. There we go. All right, so we'll get to that word problem in a minute. All right, part C, or example C. G of x, so changing functions here, g of x is 2/3 x plus 5. Find the intercepts. All right. What does it mean, find the intercepts? What kind of intercepts do we have? Y and x, that's right. It's in the slope-intercept form, so I get which one really easily? The Y-intercept. So let's do that one first. The Y-intercept is what? What's the ordered pair? 0, 5. Yeah, good job. That's right. All right. Don't have to do any work to figure that out. If it were a more complex problem and it wasn't in this form, how could I algebraically find the Y-intercept of any function? Could graph it, but algebraically would mean working something out. So what do I plug in to find the Y-intercept? X would be in the 0. No matter what kind of function we deal with from here to the end of the course, we're going to get a lot of different kinds of functions. If it asks for a Y-intercept, put 0 in for X. That's all you have to do. Since this is in slope-intercept form, we don't have to do that because we know, hey, it's 5. We don't have to do any work for that. Let's get the X-intercept. That's right. Plug a Y in at 0 and work that out. So g of x is y, so I'm going to plug that in. 2/3 x plus 5. Subtract 5. Negative 5 is equal to 2/3 x. How do I solve that? Flip and multiply. Multiply by the reciprocal. So that's going to be negative 15 over 2. So the ordered pair for the x-intercept is what? Good job. So there we have found the x and the y-intercepts. Basic stuff, been doing for years with that. We're just dealing in function notation and working our way through those things. Okay. Let's get one of those. I kind of mentioned earlier that there are some exceptions to functions that are written in linear functions that are not written in slope-intercept form. H of x is equal to the plane number 8. No x on that 8, just the 8. What do we know about the graph of that? Anybody remember, without punching it in your calculator, what the graph looks like? Yeah, horizontal line at x equals 8. Or y equals 8. Y. X equals a number would be what? Vertical. Is that a function? No. It fails the vertical line test. It's a vertical line. So, this passes the function test, so you can read it in function notation. Now let's talk about the intercepts for that. So again, y'all told me that we found x-intercepts and y-intercepts. What about the y-intercept's usually the easiest one to find. So what's the y-intercept for this? Yeah, the ordered pair would be 0, 8. The y value would just be 8. What about the x-intercept? Is there a place to plug a 0 in for x? No, so that doesn't work out. So does this one even have an x-intercept? No. We know it's a horizontal line at y equals 8, so it's never going to touch that x-axis. They're parallel to one another. So that's going to be, you just write none on that. So it's possible to not have an x-intercept. If it's a vertical line, you wouldn't have a y-intercept. That sort of thing. So basic. Kind of an additional question here. What's the slope of that one? 0 slope. Good job. Horizontal lines have 0 slope. What kind of slope do vertical lines have? It is a different word, but it's not an infinity, but indefinite. The root word of that is undefined. So undefined vertical lines have an undefined slope. Okay, so just reminding you a few things from Algebra 1, hadn't done in a while. So horizontal lines have a 0 slope. Vertical lines have an undefined slope. So this one is a horizontal line, so it has a slope of 0. Okay, related to that is what we talked about last chapter with the average rate of change. What's another name for average rate of change? Slope. It is slope. That's all it is. Remember our formula, y2 minus y1, x2 minus x1. Okay, so finding the average rate of change, if we've got a linear function, we shouldn't have to calculate it if we have the equation. What we're building up to is, what if we don't have the equation? What if we have a set of ordered pairs? And this book likes to write them in horizontal style for whatever reason. It does some in vertical, but the horizontals are the ones that usually get screwed up. So x values, let's do 20, 30, 40, 50, 60. Y values, let's do 50, 47.5, 45, 42.5, and 40. So we've got a set of ordered pairs going on there. So if I were to graph these ordered pairs on a coordinate plane, what I would end up making is a scatter plot, and I could pretty well tell that this is looks linear because the y values, how much are they changing each time? 50 to 47.5 be 2.5. 2.5 again to get to the 45. It's a pattern there, right? So if we graph these, we'd see the ordered pairs kind of going in a line. Actually, be a descending graph out of that, because as the x's go up by the same amount, the y's go down by the same amount. So that'll be like that. So we could find the equation of this line that these ordered pairs make. Okay. So how do we find the equation of a line? What's the first thing we need to find? To write the equation of a line. That would be important, but we don't have an ordered pair where it crosses the y-axis for this. So what are the parts of an equation of a line? Go back to right before we did the first example. Our function g or f of x is equal to mx plus b. So we got to find the slope and then the y-intercept. Okay, we're going to find the slope first. Now, if I give you a set of ordered pairs, I'm going to tell you which two to use. This one, it wouldn't matter which two we use because the increments are exactly the same. As we get into the section 4.2, it's more application problems, so the data set won't be perfect. You'll see a trend that looks like a line, but it won't be a perfect line like this set is. Okay, So on quizzes, I'm going to tell you which two ordered pairs to use so that we're all finding the same equation out of that. So don't freak out when you have a set of ordered pairs, and when you work the practice problems in the book, you may not get exactly the same equation if you used a different set of ordered pairs than they did. But on the quizzes, I'm going to tell you which two to use. Okay, on this one, we're going to use this one and that one. Doesn't matter which two I use for this set, but those are the two I'm going to use. I'm going to find the slope. What goes on the top? Finding the slope. Y2 minus Y1, so 45 minus 50. So how does the denominator need to be? 40 minus 20. Good job. All right, work that out. Be negative 5 over 20, which reduces to be negative 1/4. Down 1 over 4. Okay. I take that information and I put it in the place of m in my function. What do I do to find the y-intercept? You could. That would be it would end up getting you in the right spot. I don't think it's the most efficient method, but that would work. Good idea. So Luke's thinking about the graph, which is good. We got to tie all that together. We don't have the y to do that, but we do have some x's and a y that goes with them. Could I plug one of those ordered pairs in? Yeah, that's what I should do. I need to pick an ordered pair. I'm going to pick the 2050 because it looks like the easiest one. And work it out. So I'm going to plug in 50 for y, negative 1/4 times 20 for x, plus b. And I'm going to solve that equation for the y-intercept. It doesn't matter which ordered pair I use at this step to do that for this particular problem, because the slope's the same between any two ordered pairs for this problem. So if I wanted to, I usually will use one of the two ordered pairs I use to find the slope. That's always a good rule to go by. Use one of the ordered pairs you use to find the slope. Work that out. Negative 1/4 of 20 would be negative 5. And then we're going to add 5 to solve. So the y-intercept is 55. So the equation of that line, f of x, is equal to negative 1/4 x plus 55. There we go. You could check that by graphing that and then checking some ordered pairs and make sure when you plug in 30, you get something really, really close to 47.5. For this one, it'll be exactly that. So that's how you check to see if that problem is the right way. Okay. So writing the equation of a line from a set of ordered pairs. Done that before in Algebra 1, so it's not anything new. All right, let's look at this word problem here. This is actually from page 282 in your textbook. It's one of the examples. Page 282, example 4 is where I pulled this picture from. Okay. You may not be able to read it on the screen, so if you want to turn to that, you can. If you can see it on the screen, fine. That's where I'm going to go. Okay. So this problem, we read through it. It says book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate their assets using straight line depreciation, and so that the value of an asset declines at a fixed amount every single year. The amount of decline depends on the useful life the company places on that asset. So they decide how much money it depreciates by. And a lot of that is just based on over the years, we know we want to, like, if I buy a car, in this case, the company is buying cars. This is a good example of a company buying cars for their salesmen or something like that, and they depreciate the value of that car over time, so that when that car depreciates to zero, they know they're going to replace that car. That's the reason they do this. Okay. So suppose a company is purchasing a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each vehicle using the straight line method over 7 years. So their plan is for that car to last in at least 7 years. That means the car will depreciate $28,000 over 7 years, $4,000 per year. Part A says write a linear function to express the book value, capital V, of each car as a function of its age, X. Okay? All right. So, word problem with a linear equation. Okay? So, what we want to end up with for part A is a function V of X is equal to mx plus b, a linear function. That's what we want to end up with. Okay? So we've got to find the slope and the y-intercept, just like we did with the problem before. The only difference is we don't have data value, like a set of ordered pairs. But they gave us some information about how they're depreciating their car. They're depreciating their car at $4,000 per year. When you see the word per, that should trigger you to think that that number is probably what? Slope. If you're depreciating, what's the slope going to be? Positive or negative? Negative. You're going to decrease the amount. Depreciation is a decreasing. So our slope should be negative 4,000. So I'm going to go down here and write V of X equals mx plus b. I'm going to plug in the stuff I know. I know that the slope is negative 4,000 times every how many years it's been. What is our y-intercept? What was that? What does the y-intercept mean? Okay, so if it crosses the y-axis, what's the ordered pair look like? Okay, so what does the 0 represent in this situation? X, yes. What does X represent in our problem? The number of years. At 0 years, we haven't started using the car yet, right? So that's when we bought it, right? How much was it when we bought it? 28 grand. So our y-intercept is going to be that starting price. When we first bought this car, we paid $28,000 for it. So at 0 years, the car's worth $28,000. That's what our company is calling that. I know when you go buy a car and you drive it off the lot, it's no longer worth what you paid for it. But as a company, when I buy a fleet of cars, that's how I have to depreciate my values. I have to take how much money I put into it and then depreciate it from there. So for the company, when I buy that car on day one, it's still worth $28,000. Okay, so part A, this is our function that we've created. That gets part A done. Part B asks us to graph that linear function. Okay, I can do that. I have a graphing calculator. I'm going to go to y equals. I'm going to put negative 4,000 x plus 28,000. Okay, awesome. Thank you. So that's a big number. That's not going to fit on my 10 by 10 window. Yeah, no problem. Yes. All right, so that's a big number. So when I hit graph, I don't see what I'm supposed to be seeing. I know that that's not the right picture. Okay, so I need to adjust my window. Make sure I didn't have anything else going on. So I need to adjust that window to fit this scenario. So I'm going to hit window, and my X minimum, am I ever going to go into the negative years? I can't travel back in time, right? So my X min, I'm just going to make it 0 because I don't need any of the negatives. I just want to make my graph as compact as it can be. X max, 10 is probably a good number. That'll get us far enough out. Okay? Because when is this car worth nothing? In 7 years. Because that's what we've set it up to do with our business plan. Is set it up to end its value in 7 years. The scale, I'm not changing. Now, here's where the Y's go. The Y minimum, what value are we concerned about with the car? When it reaches what lowest Y value? $0, right? When the car is not worth it, we've depreciated all of its value out. So maybe an X minimum of 0. If you wanted to leave it at -10, that's probably okay. Your graph calculator can handle that. Now, what should our Y max be? Go ahead and say it. Why? That's the line. That's the most that car's ever worth. 28,000 would be at the very top. I'm going to go a little bit above that so that I can see where it's crossing the x-axis there. It makes my picture look a little bit better. So I'm just going to go to 29,000. Okay, so my max is going to be 29,000. It doesn't matter about the scale, the resolution, all that stuff doesn't matter. I'm going to hit graph now. Now I see a nice linear function for that by adjusting that graph. So I can see that. Now, on test, I'm not going to ask you to draw the graph and actually have to make the on canvas doing that. You might have to pick which graph is the right one. So understand that when those graphs are there, if it's a real world situation, then it's probably adjusted a window in some way. So you've got to be able to adjust your window on your calculator so that you can get the picture to look similar to the ones that are there. Okay, so there's our picture. I'm going to copy and paste that to my notes just so that we can see that. And go to notes and paste. Paste. And it kind of distorted it, so that's all right. So there's that nice picture. So there's the B part. It's the graph that thing. Okay. And then C part, I go back up here to the problem. It says, what is the book value of the car after 3 years? What does that mean? Yeah, plug in V of X. We're going to have find V of 3. That's what we're doing. Same thing. We're using the function to do that. Yeah, is what we're using. The same thing, same work. So I actually may use my calculator to help me do that. I'm going to hit trace 3. 16 grand. I ain't going to waste that good graph I do with that function. If you work that out, 28,000 minus 12,000 is 16,000. Always. Okay. But I did all that work for the graph. I'm gonna use it a bit. All right. Go back up here. Part D says interpret the slope. What does that mean? To interpret the slope. I don't think it'd be a guesstimate what it is, because we know what it is. We know the number that it is. Interpret means, what does it mean? What does negative 4,000 as the slope mean? Yeah, that's what that means, is that the value of the car decreases by $4,000 each year. You'd be writing out a statement. The value of each car decreases by $4,000 yearly, or each year, whichever way you want to write that. Okay. So in a business sense, you would try to, allocate $4,000 in another account so that at the end of 7 years you can buy a new car for your salesperson out of that. Okay. If that's your business plan. All right, E part. Go back up here and read what it says. When will the book value of each car be $8,000? Solve the equation. V of x equals 8,000. They give us a hint. So I'm going to take 8,000. Yeah, plug it in for V of x, just like we did on the non-word problems. Solve that. Subtract 28 grand. That'd be negative 20 grand. Negative 4,000. Divide by negative 4,000. How many years is that? 5. After 5 years, the book value of the car is $8,000. And that may be your point where you're saying, okay, if I depreciate this out 2 more years, the car's not worth anything anymore. Maybe I need to sell it and buy a new one. So, maybe that's what my plan is, to do that. So, looking for those values, important part of that. And then that's all I want. We're not going to do the F part on that one. So let's talk about one last thing. Last one. Example G, supply and demand. So business principles, we're applying all this simple linear stuff to that. So when you encounter a problem that's about supply and demand, they're going to give you a supply function. S of P. In this case, they're using P as the X value. 60P minus 900. And a demand function. D of P. And this one I pulled from a problem that talked about the price of a particular product that we were making in a factory or something like that, and our sale price of what we would make. So P represents a price in dollars. Okay, so the supply function says, okay, the supply at a certain price, we can find this with this function, 60 times that price minus 900. So that minus 900 must be like our set of the cost to get our machine to run that product, something like that, or the materials cost, something like that. That's where that minus 900 is coming from. Our demand function is a negative 15 times the price plus 2850. So we've got a supply and a demand function that we've built over collecting some data with our business, and they're going to give that to you in this section. Okay. First thing I want to find is the equilibrium price. How do you find what's equilibrium? Say that again. Okay. Kinda middle, but what are the first few letters of equilibrium? Equal. I like the word equal. So an equilibrium price will be where supply and demand are equal to one another. Okay, so we're going to set S of P equal to D of P. That's the theory of what we're doing here. So we're just going to do that math. So the supply side, we got 60P minus 900 equals negative 15p plus 2850. Good old algebra, easy math here. I'd add 15, add 900, and we get 75p is equal to 3750, and then we would divide by 75. $3.03 divided by 3/4 would be 50. The zero on the 5 with the zero in it. So $50, that price would get us equilibrium. Supply would meet demand. We sell everything we make. That's a good point. Okay. Now, question 2 from the same scenario is, what prices create a greater supply than demand? What prices create a greater supply than a demand? So that means, where is S of P greater than D of P? Where is supply greater than demand? If we set that up equation or inequality wise, we'd have 60p minus 900 greater than negative 15p plus 2850. Isn't that the exact same thing I just solved? The only difference is I have an inequality symbol in there instead, right? So I know the equilibrium price is 50. What does the price have to do for the demand to go down? If the price goes down and it gets cheaper, what happens? Right. So like if an iPhone 12 is about to come out, they're going to lower the price of iPhone 11, right? So guess what's going to be selling a lot of iPhone 11s? Because the 12 is going to be, crazy. But iPhone 11 you can get for 800. Crazy. All right. So the price, if the price gets above $50, then our demand goes down. If we put it on sale and the price goes below $50, what does our demand do? Goes up. And so when we adjust that equilibrium price, when we go above it, demand goes down. When we go below it, demand goes up. So sometimes it'll ask for the equilibrium price. Sometimes it'll ask for this situation. What price causes supply to be more than demand? That different scenarios call for this. But you've got to know, hey, I just need to set up the equation or the inequality to solve that. Not really rocket science there, but a pretty easy thing. All right, so section 4.1, really easy stuff with linear equations, but when they start applying it to those word problems, that's where it's a little tougher. Okay, so make sure you're doing all those word problems there for